In the last theorem we talked about Fermat's little theorem, which tells us that if you have a prime number p, and then you take any other natural number a, and you raise a to the p, it will be congruent to a modulo p. In other words, a to the p and a itself will have the same remainder when you divide by p. And so that turns into a nice test because all prime numbers have to work that way for any a. So if you have a number and you're interested to know if it's prime or not, one test you can do is you can take your number n, we'll call it n because we don't know it's prime yet, take your number n and then pick any number a and see if this is true. So compute a to the n, mod it by n, and see if it's the same as a. And if it's not, then you know you must have a composite number because this has to be true for primes. So this test can identify composite numbers. However, it's not a complete test. It does have false positives, and we mentioned that at the end of the last video. Just to go over that again, if we do a Venn diagram of all numbers and we have the composites separated from the primes, and let's take a equals 2 as a first example. We can take a equals 2. That's the smallest a we can take. And we look at all the ones that pass this test, all the numbers that pass this test with a equals 2. Well, of course, all the primes would pass it, because that's what Fermat's little theorem says. But some composites, a small number of composites, will also pass the test. 341 was given as an example that passes the test with a base a of 2. That's one example. So that's a problem, because if you pass the test, you still don't know you have a prime number. It could be one of these composites acting like a prime number. And in fact, we call such composites that pass the test as if they were a prime, we call those pseudoprimes. So that 341 is a pseudoprime to the base 2. Okay? Well, we can also do the Fermat's last theorem with a base of 3, with an a of 3. But again, the same thing happens. Of course, the primes always pass that test, but a small collection of composites also pass it. Those would be the pseudoprimes to the base 3. And so on. So there are pseudoprimes for every base. It is a fact that I will not prove here that no matter what your base is, there are actually infinitely many pseudoprimes to that base. So there's not a lot of them. They are rare, but they go on forever, so it's not like we can just go beyond the last pseudoprime and get past them all. They are very rare. They're rarer than primes themselves, and they get more sparse as you go higher and higher up, but there is always going to be another one. So that leaves the window open for this test failing, no matter how high up we go, no matter how high the number we are testing happens to be. If it passes the Fermat's last theorem test, we still don't know it's a prime number, unfortunately. One thing we can do is we don't have to only pick one a. We can test against multiple bases. We can test with an a of 2, we can test with an a of 3, and so on. So, for example, 341 was a pseudoprime, right? It passed the test with base 2. 2 to the 341 was congruent to 2 mod 341, as if 341 was a prime. But if we go to base 7, we do 7 to the 341, we do not get 7. We get 51, it turns out. If you plug that into Wolfram Alpha, you get 51 mod 341. So we fail the test here. Now, again, the test works when the test is definitive when you fail the test. So now that does tell us definitively that 341 is composite. So yeah, we can test against multiple bases. However, this still isn't perfect. This helps, but it's still not perfect because although in this example I gave you a number that was a pseudoprime to one base, but then we tried another base and it passed, there are numbers that are pseudoprimes to more than one base. And there even are numbers that are pseudoprimes to many bases. And then, unfortunately, there are even the nightmare scenario of composite numbers that pass the test for every base. And we call those Carmichael numbers, after a number theorist named Robert Carmichael who studied these. Some people also call them absolute pseudoprimes. So no matter what base you take, they're going to be a pseudoprime. They're going to be a composite number that acts like a prime. So we could test with many different bases all day long, and it could pass all of them, and yet we still wouldn't 100% know that we had a prime number, unfortunately. Carmichael numbers also go on forever. There are infinitely many of those, so we'll never run out of those. They are very rare. 561 is an example of a Carmichael number. So 2 to the 561 is 2 mod 561. 3 to the 561 is 3 mod 561. 7 to the 561 is 7 mod 561, or any number you take, any A that you take, it will pass that test and it will act like a prime number. But it's not. It is composite. Of course, this is a small enough number that we can just use trial division, and 3 goes into it. And it turns out 561 is 3 times 11 times 17. It's easy to factor. But it is a Carmichael number. It does pass this test. And of course, we're not concerned about these small Carmichael numbers that we could factor anyway. We could determine if they were prime anyway. We're worried about the big ones that we can't just factor. That's why we're looking for a definitive test for the really big numbers. But yes, Carmichael numbers, there are very big Carmichael numbers. And so again, to repeat myself, if you're a number and you pass the FLT test for every base, you still can't definitively be called a prime. There's an outside chance that you're a Carmichael number. Okay. So we want to we need to improve the test further, and we'll go on to that in the next video.